Alrighty, it's the noon hour and it's time to start. So, oh, I thought someone was supposed to observe me, but I guess maybe it's the 3 o'clock class. I don't know. Yeah, if you ever take a speech class, they say never apologize to the audience and never say something's boring. But I'm sorry, I think a lot of stuff I think is kind of boring right now. Like we're gonna cover naming today, and probably thinking, why would this guy get a PhD in chemistry and we're talking about naming stuff? Is that what we do all day? Sit around and name stuff? No, this is just the kind of beginning stuff. I think the fun part of chemistry is like when we have chemical reactions and try to figure out what they do, or the quantum mechanical stuff. Quantum mechanics is really trippy. That stuff's really cool. I think that's just the cool stuff. And the research is a lot of fun. You can take lasers and blow stuff up. That's fun. But like this kind of stuff, it's not as much fun. But bear with me if you don't mind. It'll get more interesting later. I'm actually getting excited about Chapter 7. That's the stuff that I like. I start to like Chapter 7 on. But up until then, it's kind of the important but boring stuff. So, okay, so we're in Chapter 3, and I know we're changing lots of topics, and we're moving kind of quickly. So we're still going to change topics quite a bit. I mean, that's why people hate freshman chemistry, the 161 class that's taught around the nation, because you have so many different mental models. I can't even think of another class that has more mental models than this one. I remember I took a Mandarin Chinese class, and there were so many mental models there. There was the calligraphy, there was the ancient and the modern, then there was the pinyin, then there were the tones, and then there was like the vocabulary. Like 5 mental models you had to master for that class. And here, I mean, we got stoichiometry is a huge one. Naming is not too big important. Gas laws, Lewis structures, like a lot of the math. And it's just a new day, it's a new mental model. And then even with the bonding, there's Lewis theory, VSEPR, molecular orbital theory, and like you're kind of expected to know at least the surface of all this stuff. So it's a lot. This is a tough class. It always feels like a sprint, at least when I teach it. It must be a very different experience for you, the students. It's been I tested out of this class when I was in college, so at least for the AP test. But anyways, well, jumping into it, we're into chemical bonding. So, and the other thing about chemistry is you'd say a lot of things that are like in the future you'll learn. In the future, you'll learn that things tend to bond to be like noble gases. So they're just particularly low energy configurations. And that's, well, we'll get into that much more later, but let me start. Well, I guess I should say the different types of chemical bonds. That'd be another place to start. Three general type. There is metallic bonding. So you can see, let me zoom in on the screen. So on the far left there, I guess you can kind of see that a little bit better. I'm going to erase this. So sodium metal, it has a metallic bond. And what happens is if you see those purple atom representation of the spheres there, the way that they bond is by a sea of electrons, meaning you have a bunch of positive nuclei here, and then depending on the metal, usually 1 to 3 electrons then flow freely between the atoms. And that's the sea of electrons. And there's a type of computing, something called the local density approximation. So if you go in to do quantum computing, not quantum computing, but quantum mechanical calculations. Quantum computing is something different. I should be careful what I say. Quantum mechanical calculations. Metals you can describe very well doing the local density approximation, which assumes electrons are this uniform gas. So having an electron just kind of flowing freely between atoms describes metallic bonding very well. We're very good at figuring out how metals work. Metals is one of the easiest things to model. And then another type of bonding is an ionic bond. Here we have sodium and chlorine, and this is where one atom gives its electrons to the other atom. So in this case, sodium is giving its electrons, 1 electron to chlorine to make chloride. And now there are positive sodium atoms and negative chloride anions, and then they're attracted to each other. And if you see, it's a 3-dimensional structure here, and you have the negative anions close to the positive cations, and so they're close to the opposite charge, but they're as far away from the like charge as they can be. And just by using the Pythagorean theorem, right? You've probably had the Pythagorean theorem before. That in Coulomb's law, you can look at the attraction between each of the spheres and the repulsion from the like charges, and from that you can figure out almost everything you need to know about ionic bonding. So it's just a lot of the Pythagorean theorem and some simple physics. You can make it a little more difficult. You can swap atoms out. You're like, all right, well, instead of a sodium atom, we'll just leave a hole there. Or maybe I'll put a cesium atom there just because I'm evil, you know. Then it gets a little more complicated, but it's still just geometry. And we could do that. That would be a very boring class. But you can describe ionic bonding really, really well, very easily. We understand that very well. And then there's covalent bonding. Covalent bonding, so chlorine, Cl2, chloride, these elements, they interact via covalent bonding. That's when they share electrons. And this is much, much more difficult. So describing covalent bonding is extremely more difficult. And of course, we say things like nonmetals engage in covalent bondings and metals have metallic bonding and or ionic bonding. Metals can have covalent bonding. They can have it with each other, they can have it with nonmetals. That's usually considered above and beyond this class, though. Nonmetals can have ionic bonding as well. So you can have polyatomic ions, so many atom ions, and they can exchange electrons, and you can have covalent, all nonmetals engage in ionic bonding. You could argue that some nonmetals have metallic bonding. Graphite kind of seems like it has a metal-like bond between the sheets of graphite, at least. So, you know, hey, what's chemistry unless we say a rule and then we contradict ourselves? Okay, so chemical bonds, ionic bonding. What I just said, opposite charges attract, like charges repel. Covalent share electrons, metallic sea of electrons. And this actually can describe many of the properties we see. So let's look at metals, for instance. So I have those dots. That's like a two-dimensional representation of a bunch of nuclei. What would happen if I took a hammer and smacked a metal and I moved all the atoms down by one? What would happen to the chemical bonding? This is what I'm trying to illustrate right here. I take my hammer and I whack it and I just move everything down by one atom. What happens? Nothing. Electrons can still flow between those, no problem. It's not a big deal. That's why metals are ductile. Ductile means bendy. So it's a type of bonding. Then ionic bonding. So I have here another two-dimensional representation of an ionic bond. What happens if I were to hit it with a hammer and then just move it by one atom? What's going to happen here? Does this mess up the bonding? Yes, it does. Now you have negative next to negative and positive next to positive. So what do you think is going to happen? This thing's going to crack. The ionic bond is going to then, it's just, if it's a rock and you hit it with a hammer, what happens? Does the rock bend? No, the rock breaks in half or whatever. Has a crack in it. Why? Just because if you just move it by one atom, you can do that. And that's why ionic compounds are very brittle. So that's why when you hit it with something, you take salt and you whack it with a hammer, you get dust. Okay, so, and we hinted at some of this last class. So calcium hydroxide here, there's this Ca, that's for calcium, OH, hydroxide, and there's the parentheses. And that 2 by the parentheses, that means there's 2 of what's inside the parentheses. So calcium hydroxide then has one of these calcium ions and 2 of these OH ions, okay, because there's a 2 next to there. So those of you in the studying human nutrition, the top molecule there, C6H12O6, that's glucose. Bottom molecule, that's sucrose. What do you call things like starches and sugars? Is there a name that we give that? It's not fats, it's not proteins. We call them carbs. And what's carbs short for? Carbohydrate. So when we started off doing chemistry, much of chemistry, like in the 1850s, was what the heck is this stuff made of? We were having, okay, what is this stuff made of? And we found out that sugars had something in common. They had a certain number. So instead of glucose, you could write that as C6H2O6. And sucrose can be C12H2O12. So we started calling them the hydrates of carbon are carbohydrates. So, but it turns out these are not really hydrates. So if you're in the chem lab, next class or next lab that we're going to have next week, we're going to look at Epsom salts. Epsom salts is magnesium sulfate, septahydrate, 7 waters. There's 7 waters trapped in the structure of magnesium sulfate and Epsom salts. There is not water trapped in sugar. So sugar, everything's connected. So they're not really hydrates. They have the formula kind of a hydrate. So it's when you're saying carbohydrates, that's actually wrong. So it's chemistry-wise, scientifically wise, inaccurate and incorrect. But we still call it that way. So the name kind of stuck. So something you might notice that we as humans, when we get something wrong, do we ever change it or do we stick with our wrong ideas? We keep with the wrong ideas. Like if you study circuits, if you take physics class and study circuits, it shows the positive charges moving. So a battery, the current is the positive charge moving towards a negative. And we know that's false. It's the electrons that move, not the protons. So, and why do we get that? Well, Ben Franklin was very involved in this, and he didn't know if the positive or negative moved. So what did he do? He guessed. And then he did everything based off of positive moving. He guessed wrong. We know we guessed wrong. Did we change our functions? Did we change our equations? Did we change our descriptions? No. We stuck with it. So that's something that, well, I guess, what it means to be human, I guess. At least we're consistent in that regards. Okay, so a lot of this is naming. I always think of Romeo and Juliet. What's in a name? But here is the simplest one. So for binary compounds, 2 different elements. So simplest one when you have 2 different elements. And this is for ionic compounds. You have the name of the cation, the metal. You keep the whole name. Okay, the whole name stays. And then the anion, the nonmetal, you take the root of the name and you plus IDE. So for instance here, CaBr2, it's so binary compound made from calcium and bromine. You call this, so to name this one, you call it calcium. That's the full name of the first metal, the first element. And then bromine, so bromine, brome, and then put IDE, calcium bromide for bromine, bromide, calcium bromide. And like if it was calcium CaO, that would be calcium, so oxygen oxide, so calcium oxide. You have the base root of the nonmetal plus IDE. That tends to be really simple. What do you do if there is more than one? I should have erased this. What do you do if there is, in the transition metals, the middle block of the periodic table, there tends to be metals that have several different ions. So what do you do if there's more than one possibility for the charge? So for instance here, so lead chloride, there's 2 choices. Lead is typically either +2 or +4. How do you differentiate that? You would name this one, so lead chloride. And I know this is a lot. If you haven't had chemistry before, you have to take all this stuff in at the same time. If you go back to the periodic table, alkalis tend to have +1 ions. Alkaline earths tend to have +2. Why? Because they want to be like noble gases. Halogens tend to be -1. Oxygen family tends to be -2. So the ions form that way. And you can tell which ion of lead it is because of the chlorine. Since there's 4 chlorines, 4 minus 1s, this means then the lead is +4. So you would write this as lead, full name lead, PV is lead, and then you call the ion, you'd say 4, but when you write it, you would write the Roman numeral 4, lead, fluor, and then in parentheses, and then chlorine, chloride. So it's lead 4 chloride. And Roman numerals, the way Roman numerals work, if you were wondering, if you want to memorize it, you can just memorize the first 10, maybe even the first 6. But goes the 1 is I, 2 is 2 I's, I is 3 is 3 I's. Well, I'm going to jump ahead. 5 is V, but 4 is 1 less than 5, so it's I before V. IV is 4, so it's 1 less than 5. 6 is VI, so 1 plus 5. 7 is 5 plus 2, VII, excuse me. 8 is 3 plus 5. Now 9 is 1 less than 10, and 10 is just X. Other ones, L is 50, C is 100, M is 1,000. So for Roman numerals. So like if you see something like 1999, that would be MCM 19, so XC IX. That would be 1999. So M is for 1,000, CM is for 900, XC for 90, IX for 9. So I think the Arabic numerals are a lot easier than Roman numerals for things. Arabic numerals is what we, the 1, 2, 3, 4, 5, that's Arabic numerals. So that's how you differentiate there if you have more than one charge. Here are some common polyatomic ions. So I'm not going to test too heavily on this stuff. I do assign some homework. I might put a few, I forget if the final has any, I think it has 1 or 2 naming questions. I don't know, I don't remember if I put any, I guess I haven't written the midterm yet, so I don't know. I don't know if I'll put a naming one on there. I personally don't see it as very important. But I mean, it's important, but it's not like, it's not the testable stuff. The concepts like stoichiometry, which we're going to learn later, that's a much more important concept to really understand and then to assess you on. But some of these, especially if you're going to go into different science classes. But at the same time, even though I'm teaching you formally here, it's also frequent. So lead chloride, I might say PbCl4. And everyone knows I'm saying, I don't say lead 4 chloride. If I say PbCl4, that's also commonly used too, but that's it's, I guess it's considered colloquial sort of chemistry language. So, and I've written up here, so I should, this is before I had my Apple Pencil, NaC2, Apple Pencils are awesome. So there's sodium acetate, so same idea for polyatomic ions. So before we were talking about monatomic ions. So if you're in a monogamous relationship, how many people are you seeing? 1, right? Monogamous, we're monogamous. What about polygamists? How many individuals can polygamists have relationships with? So 2 or more, right? So polygamy. So what is a monatomic ion is 1 atom ion. Polyatomic ion, many atoms ions. So which means 2 or more. So you can have 2, like peroxide, cyanide, hydroxide is that. So those just have 2, and you can have many. So more than 2. So their acetate has 7 atoms, for instance. So, and the idea is these polyatomic ions, they share the charge between them. So we haven't, and I'm sorry, I'm jumping ahead. Acetate, for instance, the structure, if you know Lewis structures, this is the acetate anion. and that's using Lewis structures. Leave the dots there. Are electrons dots? No, they're kind of fuzzy gases. So what really is happening is that the electron cloud around this, and it'll bunch up around the oxygens, a little bit more around the carbons too. So to an electron, if you saw the acetate anion, that's what it would kind of look like. It's a kind of Tylenol shaped with Mickey Mouse ears, fuzzy part of negative charge. So, but we'll cover more on that when we talk about quantum mechanics. Okay, so these are some common ones. So you probably, I mean, I know them all, but I don't know how many non-chemists know this stuff, even like biologists. If you ask a biologist what a perchlorate anion is, I don't know if he or she could tell you what it is, to be honest with you. So, but I'm not going to force you to know that, but there's a chart there. Okay, so now we talked about the metal, non-metal stuff. What about other things? So meaning, what about non-metals bonding with non-metals? So the way that you name them is a prefix, the name of the first element, a prefix, name of the second element, plus IDE. So similar to the metals. And the other question I get, which element goes first? It's typically the biggest and the least electronegative. And you haven't, like, what the heck does electronegative mean? Like, well, we'll find that out later. Right now, it's just going to be given to you. So you won't have to, I won't give you, like, all right, so if I have this many types of this many atoms, what are you going to name the compound? You don't have to do that. At this point in time, it'll just be given to you. And like I said, the first one is the least electronegative atom, the most metallic-like, I guess you could argue that way. And the prefix mono is dropped if the first element is only one. So, here's the prefixes. Mono is 1, di is 2, tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10. So, well, I guess, and there's some common names too. So, nitrogen trihydride, we don't call ammonia nitrogen trihydride, we call it ammonia. And water, H2O, we don't call it dihydrogen monoxide. So, except for my first lecture, or second lecture if you don't count the syllabus talk, right? So, we just have common names. And some common names sound kind of weird. For instance, ascorbic acid, anti-scurvy acid, vitamin C. You like, oh, vitamin C, that's a common name. Ascorbic acid. Ascorbic acid is a common name too. I don't know what the formal name is for ascorbic acid. That's a common name. So we do have quite a few of them. So, but as far as small molecules, it's just ammonia and water, really, I think. Well, I guess urea, that's pretty small too. But all right, so let's apply this. So this compound, nitrogen 3 iodines. So this compound, how do we name this? We have the prefix, so mono, but I'm going to say, since it's mono is the beginning, I'm going to drop it. Nitrogen triiodide. So, and the other thing with naming compounds, and you have a spell checker on Word, you're going to see a bunch of squiggly red lines over everything. So the spell checker is not going to know what nitrogen triiodide is. So, and the parts here, you drop the mono because it's the first. So so you use the first full name of the element, nitrogen, and then the same thing, root of iodine, so triiodide, then the 3, and then for the tri, and this iodine, iodide. And then for same thing for B, so we're going to drop the mono, this is phosphorus. phosphorus, and then the 5 is pentachloride. So, and I'll do purple, what the heck. Then for this one here, we're going to have the tetra and the deca. So, naming this one, this is going to be tetraphosphorus. My H's. For us, decasulfide. So that's a long word, right? So tetraphosphorus, 4 phosphoruses, decasulfide, 10 sulfurs. So how are we doing so far? Questions, anyone? Okay. And here is the summary of that. So here is how we name things. Ionic, use the metal and then the metal plus the ion. So if there's more than one possibility, use the charge of the ion in parentheses. So, and this is also the contemporary way to do it. There's an older way to do it. We would name each ion individually. Like copper can be +1 or +2, and one's cupric and one's cuprous. I don't remember which one is cupric and which one's ic and which one's us. And there's same with ferric and ferrous. One's +2, one's +. I don't remember which one is what, to be honest with you, because they got rid of that convention when I was learning chemistry. My dad would know. He was taught that convention, and you can look it up and if you look up the SDS sheets or MSDS sheets, the safety data sheets, they'll tell you the names in there. Okay, and molecular we just covered. Prefix, name a first element. Prefix, name a second element. With the exception, you drop the prefix for the mono if the first element is 1. Not the second element. So carbon, oxygen. So 1 carbon, 1 oxygen is carbon monoxide. It's not monocarbon monoxide. It's not carbon oxide. So the second, if the prefix is mono for the second element, you keep it in there. Okay, and what we didn't cover were acids. Binary acids, you have the hydro, start off with hydro, base name of nonmetal, plus ic acid. So for HCl, so that's chlorine acid, so it's hydrochlor, then ic, so hydrochloric, then acid. So then the next one is oxyacids. Oxyacids contain oxygen. And what is hard about this one is that, so the different ions, there's 8 and 8 acids, and there is no convention over which ion is 8 and which one is 8. So, for instance, sulfate is SO4. Okay, that's sulfate. Sulfite is SO3. Now, chlorate is ClO3. That's chlorate, and chlorite is ClO2. So you can see here that there's not one. They're not matching. So, and nitrate is NO3 as well. So this is another reason why people were not happy about this, because they're like, oh, there's so much memorization. So if you go back up to this polyatomic ions list, right? So you have chromate. There's no chromite, but you have nitrate, nitrite, and then there's the per. So you see, I'm pointing the screen. You have chlorate and chlorite, and if you have one more than chlorate and then the 8, it's per. You put per in front of it. And if you have one less than ite, you put hypo in front of it. So that's the other convention name that the book doesn't even cover. So if you read the book, it doesn't cover that. And for oxyacids, for chlorate, you use the ic, You don't put hydro, you just put the ic. And then for the ite ion, you use us, still not using hypo in front of that. So it has phosphoric acid there, but for sulfate, so H2SO4, that's sulfate acid, that'd be sulfuric acid. And SO3, H2SO3, the ite ion, that would be sulfurous acid. And not listed in the book, so we have chlorous and chloric, but then having an extra oxygen, that would add per on that, so perchloric, and then one less oxygen than the chlorous, so it would be hypochlorous acid. So I guess, well, hypochlorous acid, bleach. I like using bleach for a lot of things. I use to wash my clothes, and anytime there's a stain on anything, I use bleach, or to sanitize things. That's sodium hypochlorite, NaClO. So hypochlorite, it's used commonly, at least I use it commonly. But then you can, the acid there, so hypochlorous acid, like that. So how are we doing so far? Any questions? Hopefully I'm not boring you guys to death. Yeah, questions?
Is this chart something that we should really pay attention to?
Of course, everything is kind of like asking the waiter if everything, if what's your, is this item on the menu a good dish, kind of thing. But as far as for the point to effort ratio, study more stoichiometry than this. It's important, but I mean, it's not like there's going to be less tested stuff on here. And the other thing is, if you take a test with me, you haven't taken a test with me yet, I allow questions that are kind of clarification questions or definition questions. And unless the question was about naming and you asked what the name of that was, I would tell you. Or if it said hypochlorous acid, what's hypochlorous acid, I would give you the formula. So at least in my class. So the caveat would be for that, if the question was asking, what's hypochlorous acid, I wouldn't tell you. Does that make sense? So in tests, I don't answer strategy questions either. So like later on, we'll learn about the gas law constant R. Okay, and there's a couple different values for the gas law constant R. If you ask me what's the gas law constant, I'll say it's R, or what's R, and I'll say that. And you can ask me what the units, and I'll even give you a sheet that has the units on it. I just point to the sheet. If you ask me which value of R I should use, I won't answer that because I consider that to be a strategy question. Does that make sense? Okay. So for this class, well, I guess I'm on YouTube, but the heck, it's not that important. Vlogs, hi today. Other questions? But it's important enough that I spend a half an hour talking about it, of course. Okay. And out of curiosity, raise your hand if this is not review to you. Is this all new to you? So some of you, okay. We have a couple of people. So about a fifth of the class had never seen this before. Okay. All right. So you didn't have chemistry in high school then, or your high school just didn't cover it? Okay. All right. So if that's the case, be sure to read the book. That's going to be important. Or listen to if you don't learn by reading, then watch my lectures again, kind of thing. Okay, so formula mass. We've already talked about the mole concept a little bit. So remember, a mole was the chemist's dozen, right? That we use a mole to describe a huge number of things that atoms take up. So now we're going to talk about how to get the formula mass from that. So and the way that you do this, it's the sum of the number of atoms of the first element times the atomic mass of the element plus the number of atoms of the second element times the atomic mass, and so on. So let me illustrate this here for glucose. And I'm still at purple. I like blue. So calculate the formula mass of glucose, C6H12O6. So if you don't know what glucose is our primary fuel. So humans' primary fuel, we can burn fats and proteins as well, but we like to run off of glucose. So, and that's the way it is for most living creatures on Earth, actually. Most living, not everything, but most do use glucose. I mean, yeast can, of course, well, I guess they do use glucose, but they do fermentation with that. Anyways, as can we. Okay, so C6H12O6, and I apologize if this is all review for some of you. The subscripts mean numbers, so the 6 underneath the carbon means that there's 6 carbons. The 12 underneath the hydrogen means there's 12 hydrogens. The 6 under the oxygen means there are 6 of those. So the formula mass for this, you take 6 times 12.01 for the carbon. So I guess and then 12 times 1.008 for the hydrogen, plus 6 times 16.00 for the oxygen. Where am I getting this from? I guess I already color-coded some of this before. I'm getting that from there, and I do apologize if anyone is colorblind. Let me describe what I'm saying for the colorblind, and then the 6 comes there for that, 12 comes there for that. Okay. So the 12.01 is the bottom number for carbon on the periodic table. There's 6 of them. That comes from the subscript there. So 6 carbons. Carbons have the average mass of 12.01. Hydrogen, there's 12 of those times the average mass for hydrogen, 1.008. And then 6 oxygens, average mass of oxygen is 16. So you get that. And put in your calculator. I know it's 180. Some of them I just have memorized. I know water is 18, ammonia is 17, carbon dioxide is 44, glucose is 180, sucrose is 342. For this I'll just go ahead and calculate it out that way. So 6 times 12.01 plus 12 times 1.008 plus 6 times 16. And this is 180.16, and the units are grams per mole, grams glucose per mole. I'll go ahead and take a picture of this. Oh, the glare on the screen. All right, oh, the glare. There we go. All right, so, and you'll see, I'll do this very frequently. With glucose, I'll just call it 180 grams per mole. What that does, the term is called truncate. You chop off the ends. So frequently people do this, and you can truncate terms, chop off the ends, and that introduces error. That's also, the error it introduces called truncation error. So, it depends on your sig figs, depends on your applications. So, but glucose there, 180 grams per mole. So recap how to do this. You look at the formula, glucose C6H12O6, 6 times carbon plus 12 times hydrogen plus 6 times oxygen. You add them together to get the 180 grams per mole. Does anybody have any questions on how to do this? Okay. So let's do another one. Aspirin contains 325 milligrams of acetylsalicylic acid how many acetylsalicylic acid molecules does it contain? This is another one actually I have memorized. This one is also 180 grams per mole. Raise your hand if you want me to calculate that out. Okay. So aspirin is 180 grams per mole, or acetylsalicylic acid. And let me change the blue again. So 325, how many acid molecules do you have? So I might just put 0.325 grams. If this bothers you, I can do 325 milligrams and then do gram to 1,000 milligrams. So you can insert that step there, but I also have the habit of skipping certain steps. I would just take this and I would just, instead of 325 milligrams, I see this as 0.325 grams. And then just go, but I'll keep the units. I'm just saying AS for aspirin. Maybe I'll just say A. A for aspirin. So 325.325 grams of aspirin, and then we have mole of aspirin to 1,880 grams aspirin, and then how many molecules? 6.02 times 10 to the 23rd. Okay. So at this point in time in chemistry class, A is just aspirin. I don't really want to write acetylsalicylic acid. That'll take too long. So 325 milligrams, this is 0.325 grams. The molecular weight here, the grams aspirin cancel, then the moles aspirin cancel, and we're left with molecules. I'm getting a lot of questions from my online students about these stuff. Okay, I will go ahead and take this photograph. Does that block anything? No, okay. Not blocking anything up there. So if you want to follow what I did later in the calculator, you can see that there. Put in your calculator, you get, how many sig figs we have? 3. 1.09 times 10 to the 21 molecules aspirin. Okay. So recap for this. We have 325 milligrams of aspirin. How many molecules is that? So good way, like I said, with chemistry class, think about moles. So we're going to use dimensional analysis, convert the mass to moles, and then moles, we do the number, the Avogadro's number, 6.02 times 10 to the 23rd per mole. And from that, we can calculate the molecules outright. So questions? All right, time for you to do something. How many ibuprofen molecules in a 200 milligram tablet? So carbon, it's 12. Hydrogen, it's about 1. Oxygen, it's about 16. So this is your chance to start doing this. But can anyone figure out the answer just by looking at it, though? Can anyone do that? Can you get rid of 2 answers without just looking at it? So 325 milligrams, we had 1 times 10 to the 21 molecules, right? That's a lot of molecules. Are we going to have 206? No. C is garbage. So molecules, chemistry, we deal with discrete mathematics. 1, 2, 3, 4, 5, whole numbers. Can you have a fraction? Nope. These two are garbage. So when you're taking tests and you're looking at answers, get rid of the ones that don't make sense. These two are the only ones that make sense. And based off the previous answer, which one do you think it is? I can guess. We'll see if I'm right. Okay, so if you're wondering what to do, the first thing you have to do is calculate the molecular weight of ibuprofen. So go ahead and start, if you want, start talking to the person next to you or behind you, that kind of thing. Is anyone completely stuck? Has no idea what to do? Raise your hand. Okay. Because that's when I come around and talk to people.
Carbon times 13 carbons in. I'll just send it already as well. Draw. Each way 12, 13. And hydrogen is 1, so plus oxygen, there's 2 oxygens and 16 each. That's why the 2 to 6 is on there. That's how much it weighs per mole.
Oh, that's very accurate.
Yeah.
Oh, it's flat. So then the separate mass. That's the
Yeah.
of the. Okay, so that goes there.
So we have 12 carbons, no, 13 carbons at 12 grams plus hydrogen is 1 gram, and there's 18 of them, plus we had 2 oxygens at 16 grams of hydrogen. Does that make sense? That's how much the molecule weighs per mole.
Divided by 200. That's going to be so just by
Okay, so now for there,
1,000
weight times grams because they both is your grams. Cancel each other out. So we cancel it out and divide that top number by the bottom number.
You see this?
We cancel them out. Multiply this by this, so this becomes 0.2 moles over 206. So that's how many moles you have. That was our last period. The grams, if you have grams per mole, that's what that means. 206 grams per mole, but we cancel grams out, so it's just 206 moles.
E? Oh, the extra. The element of surprise.
And that's how many moles there are. Now we convert the moles to atoms. So we times that number.
Yeah, you got that. That's right.
So we use the formula just to get.
Yeah. How do you get 206?
This one. That's the.
You wouldn't have it, but
Yeah.
so you have 13 carbons. 13
No.
times 12 carbons
Alright, we do.
plus
Oh, the grams.
times 1 for times 1 for the hydrogen, and then 16 times 2 for the oxygen.
We need that number to times this number. Drop these.
So can you put that? You got it. Yeah, that's right. Did you have it correctly?
And then times 10. That 5.
That's right. It's good. You got it.
This one is better. So that's
All right, I think everyone's, from what I've gone around, everyone's converging on B. And that's, I'm not going to ask them, but that's the proper answer. So, what I was kind of hitting at before, since we just did this one, and it was 10 to the 21, and that's closest to B. That's why I thought, I mean, I kind of look at it like, oh, it's probably B. Even without using your calculator, you can, like, you ever gone to office hours and you bring your homework and you say, this is the answer I got, and the professor's like, does it make any sense? It's like, is it the right answer? Does it make sense? You ever had that argument with someone before? Sometimes what we're trying to say that is you can look at something and not use a calculator. So I can look at this, 0.2 divided by 206. In my head, that's about, so this is about 1/1000th. So this is about 1/1000th, and then I can take this and then subtract 3 from the exponent. So in my mind, I think, okay, the answer is probably around 6 times 10 to the 20. So that's called using a order of magnitude calculation. So any number that's close-ish to 6 times 10 to the 20 is going to be the right answer. So then you could do this without even using a calculator, especially the multiple choice test. So that's also a way you can check your answers, is by using a order of operation. It's like, does this make sense? Because sometimes you're putting numbers in the calculator and you miss one. or you miss a decimal point, and you have something that's 100 times what it should be. Then like if you're doing an order of magnitude calculation in your head, you're like, wait a second, that's wrong. Okay. So, how many atoms do we have in this ibuprofen tablet? I know there's ibuprofen's got like, depends on what you have. You have a liquid tab, it's gonna have water, it's gonna have the whatever gelatin or whatever heck the liquid tab is made of, or if it's a pill, it's gonna be starch and the candy coating or whatever. But let's just look at the ibuprofen, and we already have this. There's that many molecules. How many atoms is that? I guess I should. How many atoms does ibuprofen contain? 13 carbons, 18 hydrogens, and 2 oxygens. How many atoms is that? 33. So how do we solve this one? You have the number of moles. It's 5.8 times 10 to, or the number of molecules, 5.8 times 10 to the 20th. You multiply that by 33. So that's like 6 times 10 to the 20th, and 33 is kind of like 30. What would 6 times 30 be? That'd be 180. So it'd be like 180 times 10 to the 20, or 1.8 times 10 to the 22. That's close to 1.9 times 10 to the 22. So you can do these in your head. Are you following my logic there? My brain logic? Or you could throw in your calculator. That also doesn't fail. Right? So if you take 5.8 times 10 to the 20 times 33, you will in fact get 1.9 times 10 to the 22nd. Just two sig figs. All right, so how are we doing some more questions? Okay. What else can we do? And it's good to get to this because you're going to do this in lab on Monday or Wednesday or whatever day you're doing lab. So what is the mass percent of chlorine in Freon 112, which is C2Cl4F2? So freons are a series of compounds called chlorofluorocarbons. So celebrity Jeopardy question here. What 3 elements are in chlorofluorocarbons? Chlorine, fluorine, carbon. Chlorofluorocarbons are made of chlorine, fluorine, and carbon. So we are getting rid of CFCs and we're using hydrofluorocarbons instead. Can you tell me what 3 elements are in hydrofluorocarbons? Hydrogen, fluorine, carbon, right? So some of these names make sense. So for me, I don't store things in terms of like memorizing them. I attach them to other things. So I don't think CFCs, oh, like it's like a flashcard. CFCs, chlorofluorocarbons, chlorine, fluorine, carbon. I look at the name and I associate that. So these are CFCs, chlorofluorocarbons. They're great molecules, great molecules. They're very, very safe, but they damage ozone, unfortunately. So we don't use them as much anymore. Okay, so mass percent of chlorine in C2Cl4F2. So we look at the periodic table, and so the percent of chlorine, kind of like, you ever done like body fat percentage calculations? What's your body fat calculation? Well, that's how much fat you have over your total mass. So if you're 20% body fat and you weigh 100 kilograms, that means you have 20 kilograms of, I used to say mass, sorry. If your mass is 100 kilograms and you have 20 kilograms of body fat, that means you have 20 fat over total mass 100, you're 20%. So how do we figure out the percent chlorine? We get the mass of chlorine over the total mass times 100 times 100% to give you the total. This is considered to be chemistry common sense. So if you're saying what's the percentage in this, like what's the formula for the percentage of something, it's considered that you would understand how to do this without having a formula to prompt you. So there are other formulas that we'll have that you'll, like the Rydberg states. We'll cover that in chapter 7. You need the formula for that. I'll give you the formula for that. But for this, would not. I probably, if you asked me in the test, I probably would tell you. But it would be kind of like, it's probably more, I would hope it's more that you're just really nervous and you forget something. So sometimes students do that. They get test anxiety and they forget how to tie their shoelaces during tests. So, but okay, so mass percent of chlorine. So the mass of chlorine, so it's going to be 4 times 35.45. That's the mass of chlorine on the periodic table. I have it memorized. You probably don't. But chlorine there, 35.45. Fluorine is 19. Carbon is 12. So you don't have to have them memorized. I don't know what the atomic masses of ruthenium, for instance. I don't have them all memorized. I used to do research with chlorine, so I know that pretty well. So that's the chlorine. And then carbon, 2 times 12. I'll zoom in. 2 times 12 for the carbon, plus then the 4 times 35.45 for the chlorine, plus 2 times 19 for the fluorine. And you just put that in your handy-dandy calculator. 4 times 35.45 divided by 4 And again, I'm skipping the step that the fraction is 0.696, but I'm just going to say it's 69.6%. Does anybody want to see the calculator? Raise your hand if you want me to put the calculator up. Okay. So, and again, this is just the mass of the chlorine, and you get that from the bottom number in the periodic table. I guess I have the periodic table up here. So chlorine here, 35.45. Fluorine's 19, carbon's 12. And so the mass of chlorine over the total mass, and then 3%. Does anybody have any questions on how to do this one? Okay, so how much hydrogen can we get from 1 gallon of water? Okay, so there's some backstory with this stuff. We are looking to have alternative fuels, and one of the problems is gasoline is just about as perfect fuel as you can get. So gasoline is relatively non-toxic. It's got a long shelf life. It's really stable. And it's really jam-packed full of energy. And it's cheap. So like the just piles up the reason why we use gasoline. So what do I mean by that? So gasoline, so if you look at ethanol, for instance, ethanol has about 2/3 the energy of gasoline. So kind of like what'll get you more fat? A pound of broccoli or a pound of butter? Like butter. Why? There's more calories in butter than broccoli, right? And what do calories mean? It means energy, right? So gasoline is jam-packed full of that. And gasoline also is relatively non-reactive. Like you'll see cars now, E85 cars, for instance, 85% ethanol. A normal car engine runs off of E85. The difference is the tubing. The ethanol will dissolve the tubes. And the same is true for biodiesel. So there's not really anything special about a biodiesel engine. It's just the tubes are different in the fuel lines because the biodiesel will gunk up the gunks up the fuel filter for both the gasoline engine and the biodiesel. If you switch them over, you'll probably have to change your fuel filter very frequently because it'll dissolve the fuel lines. We have to handle ethanol and other things a little bit more carefully. And hydrogen, well, if you get into a car accident, I've got into, I guess only 3 in my life, and I've seen a few. Never have I ever seen a car explode like they have in the movies, right? Why? Well, in part because of our fuel. If we put hydrogen in cars, though, if we don't store it properly, if you hit the hydrogen tank, that thing's going to go off. It's rocket fuel. It's extremely explosive, and it's a gas. So, but hydrogen, we do use hydrogen for some fuels. Like I said, rocket fuel. I remember Arnold Schwarzenegger when I was in California when he ran for governor. He's like, "I'm going to run my Humvee off of hydrogen." I was like, "Well, thanks, Arnold. Just tell me how rich you are, you know." Takes a lot of money to do that. Hydrogen, this is not how we get hydrogen. We don't get hydrogen from cracking water. I think the only time that we would crack water to use it for something is in nuclear submarines. So in nuclear submarines, there's lots of electricity, not that much air. How do the sailors, how do they breathe underwater? Well, they take water and they crack it into hydrogen and oxygen. When they breathe the oxygen, they dump the hydrogen overboard. And then the hydrogen just dissolves in the ocean. So, but we don't get hydrogen this way. The way that we get hydrogen is either by doing something called steam reformation. We take steam, so H2O water, and we react it with methane. So reacting steam with methane will form hydrogen. The other thing that we can do is we can do reforming molecules in oil refineries. Specifically, we cyclize them. So hydrocarbons tend to be long chains. We can cyclize them, and when that happens, hydrogen pops off. So those are the two ways. Usually, the hydrogen popping off on the cyclizing of the molecules in a refinery. That's more the hydrogen's a waste product. And refineries usually just get rid of it. They usually burn it or they dump it somewhere. When we want to make hydrogen for something in an industrial process, usually steam reformation is the primary usage. So, and of all the processes, probably ammonia synthesis, making ammonia from air, is where we use a lot of hydrogen for. And that's typically done with steam reformation, like I said. So, and wind energy. So let's compare wind power to water power. So hydroelectric. Has anyone ever seen the hydroelectric plant in the Big Island? And no one's ever seen a hydro plant. Are they big or small? What do you think? Tiny or small. So why? Well, because water. So the way they work is water turns a turbine and a generator. So the alternator in your car is a generator, and any other generator. All it is, you have a wire and you have a bunch of magnets that spin around the wire. Okay, and typically here in the United States, we spin it at 60 times a second, so 60 hertz. Europe, it's 50. So we spin a magnet around a wire at 60 times a second, and that induces a current flow in the wire. That's our alternating current at 60 hertz. And what we do then, so same idea of the hydroelectric plant, use the water to spin a wheel, and that wheel, through a bunch of gears, then turns a generator. And then you get electricity that way. Same thing in your car. I don't know what frequency they use in an alternator. It doesn't necessarily have to be 60. But the alternator is just the same way. So a wind farm, same idea. When the wind blows the turbines, it is same thing. Magnets around a wire generate electricity that way. So wind, we have the windmills on this side of the island. Are they big or small? They're huge. Windmills are huge. Hydroelectric plants are small. Hydropower is very consistent because density of water is very consistent. Wind power is it's not very usable because it's, number one, it's really, air is thin compared to water, so you need to have huge turbines, and then also the output is not consistent. So, and throwing an inconsistent output into a grid makes it really cumbersome. So how do you make the output of wind usable? Well, there's a couple ideas, like, well, water is really usable. Why don't we use the windmills to pump water uphill and then drop the water and then have that turn a turbine? Now we have a really consistent energy source that way. And why don't we do it that way? Well, because you lose so much energy pumping the water uphill. There's too much loss, too much entropy, heat loss in that. So like, oh, what if we convert it to hydrogen and then use the hydrogen for that? This is still not a good thing because, well, when we do the calculation, you'll see that you make a lot of oxygen, by mass, you make a lot more oxygen than you do hydrogen because water is 1/9 hydrogen and 8/9 oxygen. So this is impractical. We won't do it this way. We probably won't ever do it this way. And if we ever do it this way, it's to make oxygen for people to breathe. So, but it's a good idea. We're getting there. Alternative fuels, I guess we only have 3 minutes left, so I'll talk a little bit. I've done some research in this. I was a consultant for a company for a bit doing alternative fuels. One of the fuels that we're looking for is butanol, so 4 carbons OH. And that one's getting close to the energy level of gasoline. It's also a liquid. It's easy to handle. Liquids are easier to handle than gases, right? So if you open up the cap on a gas, all the gas escapes, right? So you open a tank of gas and gasoline, all the vapor. Of course, if you leave it, open up the top, leave it out in the sun, yes, it'll evaporate. But I mean, just sitting there, open up the can and pour it somewhere. Liquids are super easy to handle. And there's been a lot of think tanks about this. So not a problem here, but on the US mainland, if you ever drive a long distance, they tend to have the exits about 30 miles apart. And the reason for that is if your check engine, like if your fuel gauge goes off in your car, and you're like, okay, you need to refuel your gas tank, you have enough time after your fuel light goes off to refill your gas tank. So there's a reason why they have it that way. And the government has hired a bunch of people like, all right, let's have ethanol instead of gasoline or something like, or methanol. Ethanol has about 2/3 energy. Methanol has 44% that of gasoline. So meaning if you can drive 200 miles in a tank of gas, you could drive, so 2/3 of that, you could drive about 120. What's that? It's 132. 132 miles on your tank of ethanol. If it's methanol, it would be 88. So a tank of methanol will take you 88 miles. So they said, like, okay, well, if we're going to replace the fuels, we either have to change the drivers, retrain them to refuel more quickly, or we have to have twice as many exits on the freeways, or we'll have to raise the bar to the check engine light on the car. Because the way that typically a gas engine works, there's a float in your, literally it's a piece of plastic. I've changed a fuel pump in my car once. It's a white boat that's about this long. It's a piece of plastic, and it floats, and it's connected to a bar, and then that's your fuel gauge. How high that thing is, that's your fuel gauge. If it drops below a certain point, then your fuel light goes off, of course. So there's other complications of the fuel pump. It cools off by the fuel. So if you continually drop your fuel level in your car, your fuel pump will go more frequently. So that's another problem. We might have, if we change our fuel type to a lower energy one, we might have more broken fuel pumps. Okay, that's my shut up alarm. All right, we'll pick up here next time. Hope you like the chemistry and society stuff alongside the other things.